Hello, Earth Science students. This is Dr. Hurt. Welcome to your now 16th lecture in Earth Science. We're going to be talking this week about plate tectonics. So we're going to spend this whole week on plate tectonics and move on from there to earthquakes and volcanoes next week. And after that, we're going to get to weather. And after that, we're going to get on to 1 week of astronomy, so you can learn a little bit more about the night sky. And that's all we have left in the class. So, you know, I think we're maybe a little over halfway done. But anyway, we'll get right on with the material here today. So know that you're busy, and I will try to use my time wisely here. So anyway, you might know and have heard in grade school or high school that Earth's surface is broken up into all these different plates. So the North American plate is the plate that you are on right now here in South Texas. So that's one plate. There's the Pacific plate. There's the South American plate, Eurasian plate, right? There's lots of different plates down here. And in fact, there's even more than what is shown here. Some of them are very small, like the Cocos plate and the Nazca plate, the very, very small Juan de Fuca plate, which is being actively subducted right now in the Pacific Northwest. But anyway, the point is here is that we're broken up, Earth's surface is broken up into these plates. And this kind of realization came about not really too long ago, in the 1960s. And I'm going to explore today, where we're going to go into great depths, the history of plate tectonics theory, where it came from, and a little bit about what it is. And then next lecture, we're going to go really into a lot of detail about what plate tectonics theory really states. Okay, so without further ado, I'll get into this. Just to kind of give you some background that's very necessary to remind you of some things that we learned very early on in the course. So we have to remember again, kind of go back to those days we're talking about Earth's structure, basic structure. And I said that those lectures are some of the really the most important lectures in the whole class, is Earth's basic structure. So remember that we have a mantle, okay? There's our mantle. Actually, it starts up here. And we have a crust, and the crust is very thin. And we have a lithosphere, and we have an asthenosphere, okay? And most of the mantle is asthenosphere, but there's a small layer here that is lithosphere, okay? So, oh gosh, that doesn't really look very good, huh? So hopefully you remember that stuff. So right here is the lithosphere. And remember that lithosphere equals the crust and I'll put and in capital letters, and uppermost mantle. Okay. So it's both crust and part of the mantle. Okay. All the mantle that comes underneath of it, underneath the lithosphere, is asthenosphere. Okay. And asthenosphere just consists of mantle. The compositional difference between lithosphere and asthenosphere. Is there a compositional difference? Okay, is there any difference in terms of composition, in terms of the elements that, in terms of lithospheric mantle and asthenospheric mantle? Is there a compositional difference? The answer to that is no. If you sent the lithospheric mantle to a chemist and you sent the asthenospheric mantle to a chemist and you didn't tell him what it was, he wouldn't be able to tell the difference between the two, okay? So it's a difference in the mechanics of how that material behaves, okay? Whether it's kind of like silly putty and moves and bends and deforms, that's the asthenosphere, or if it's like kind of a typical rock where it's cold and brittle and breaks, okay? So there you are. Here's kind of a diagram, very good diagram, shows you the crust and the mantle. Remember that the ocean crust is very thin. It's relatively denser, okay, than continental crust. Continental is less dense, right? Now, below each, the ocean crust and the continental crust, there's the lithospheric mantle, okay? And now, of course, both the crust, ocean and continent, is part of the lithosphere. But below the crust, then you get the lithospheric mantle. Okay, and lithospheric mantle again is it's strong, it's brittle, it's cold, it's like hard rock. Whereas the asthenospheric mantle is kind of the weak mantle below the asthenosphere. It is near the melting point, but it's not melted. And it is capable of moving and bending and folding and convecting. Okay, so lithosphere does not know convection. Okay, so there's no convection there. So this is a diagram that shows the depth in the Earth. Okay, there's your depth, and here you have the temperature. There's two lines. So the black line that you see is the actual temperature of the Earth, and the red dashed line that you see is the melting temperature of the Earth at that particular depth. Okay, because there isn't just one melting temperature for the Earth. Okay, it depends how deep you are, what the pressure is. Melting temperature depends on pressure, and it depends on the composition, what the rocks are made of. But suffice to say, you'll notice that in the lithospheric part of the mantle, there's this big gap between the melting temperature and the actual temperature. Okay, so it's well below, the rocks there are well below their melting temperature. For most of the asthenosphere, however, that it's very near the melting temperature. In this zone called the low velocity zone, the LVZ, there probably is a small amount of partial melting right there at the mantle. And this is actually where most of the melts of the mantle are generated, right here in the LVZ. It's called low velocity zone, LVZ, because seismic waves that go through the mantle, which, remember, I hope you recall that I talked about, that's the only way that we know about the mantle and what the mantle and the core and the outer core are made of, through seismic waves, analysis of seismic waves. Those seismic waves are particularly slow there because it's going through a little bit of liquid. There's a tiny bit of liquid there instead of solid rock. So that slows down the seismic waves. That's what we call it, low velocity zone. So the stiff lithosphere moves kind of like rafts being passively pushed around by the softer asthenospheric mantle convection. Okay, remember that lithosphere does not convect, whereas the asthenosphere does convect. Whoops, I'm trying to write does. There we go. So we have asthenospheric mantle convection that pushes and kind of responsible for the movement of the lithosphere. And of course, movement of the lithosphere is what plate tectonics is all about. The plates are kind of moving, drifting along as the asthenosphere underneath convects. Okay, so another thing I wanted to show you guys here, just reminders of stuff that we have covered, but just want to make sure that you know and remember this stuff. Age of the ocean crust versus the continental crust. So the continental crust is actually very old. Okay, it's probably around average age. Average is probably 2.5 billion years, 2.5 GA, okay? So 2.5 billion years is probably the average age of continental crust. The average age of ocean crust is no older, it's less than 180 million years, okay? It's probably averages maybe around 75 or 100 million years. So it's relatively thin, it's relatively dense, and it's relatively young, okay? So this is a really common question on the final exam. Is, I ask you to compare and contrast continental crust and ocean crust. And I've done this, I think I did that on the midterm as well. So you should be prepared for a question like that. You should just remember that ocean crust is young, it's thin, it's relatively dense. Continental crust is older and relatively lighter and thicker as well, okay? So there's a continuous, the reason that ocean crust here is so young is because there's a continuous recycling of the ocean crust through the process of plate tectonics. So Earth is a very active planet. It's constantly recycling. It's constantly, the plates are going down and subducting into the Earth, and they're coming back up again at mid-ocean ridges. Okay? Hold on one second here. Okay, sorry for that. I got interrupted. My daughter wanted to come into the room. So anyway, let me get rid of that there and continue along. So just kind of give you an overview of plate tectonics theory and how it works. We're going to get into all the details about this over the next week, but just kind of overview of the theory. So in plate tectonics theory, the lithospheric plates, okay, that's the ocean crust and uppermost mantle, are drifting along you know, they're moving over the surface of the Earth, and they've changed radically their positions over time. So there have been times in which North America was near the equator. There have been times in which South America was near the equator. There's been time where, I'm sorry, not South America, Antarctica has been near the equator. Obviously, South America is at the equator right now. But there's, you know, the continents have not been stable over Earth's history. They've moved around a lot. They are moving on the convective currents of the asthenosphere as the asthenosphere convects. The ocean crust and lithosphere is destroyed at subduction zones where the lithosphere sinks back into the mantle, and it is resurrected over here, recycled, if you will, over here at the mid-ocean ridges. I'm going to write MOR here for mid-ocean ridge, what are also called spreading ridges in the middle of oceans. Okay, so this whole cycle of subduction, of the, if you will, the death of the plate and the resurrection of the plate here at the mid-ocean ridge, and the convective currents that flow from that, moving the lithosphere along, that's kind of plate tectonics in a nutshell. Okay, so the lithosphere, the outermost 100 to 200 kilometers of Earth, the strong mantle plus the crust, is rigid, it's mobile, it drifts along kind of like a raft on these convective currents. And the tectonic plates are sections of the lithosphere, okay? The interesting geology happens when tectonic plates collide or break apart. So really, when we study earthquakes and volcanoes next week, we're going to be looking at all the things that happen at the boundaries of the different plates, because the inside of the plates are pretty boring. The boundaries of the plates are interesting. It's where the exciting geology happens, okay? So the asthenosphere is weak, is the weak upper mantle below the lithosphere. It deforms and flows easily and enables plate tectonic motions, okay? I remember I asked a question. This might have been to my other class, but you know, I asked him a question. I think it's on your lecture assignment, like, what powers plate tectonics? And a lot of people were saying, oh, it's the asthenosphere, and it's not the asthenosphere. You know, plate tectonics, convection takes place in the asthenosphere, but it's the plate tectonics, the plate motions are really being powered by convection of the mantle, okay? And convection of the mantle, like, why does convection of the mantle happen? It's merely because down at like the core mantle boundary, so the CMB, the core mantle boundary, it's like 4,000 degrees Celsius, if not 5,000 degrees Celsius. It's really, really hot. Up here, you know, it's maybe at the base of the mantle, it's probably around 1,200 degrees Celsius. So it really gets cool as you move up. And it's just that hot material is trying to rise, and it's causing that convection to occur. Okay, so plate tectonics is really all about Earth trying to cool itself off. It's just like, you know, your body cools itself off. It needs to cool itself off sometimes. Sometimes your body gets too hot, and it cools itself off using sweat, right? So sweat comes out on your skin, it evaporates, it takes the heat, excess heat away from you. It's a really, by the way, a really efficient system of cooling, much more efficient than the other animals in the world, right? So we're one of the few animals that sweats. It's a very good system of cooling. You can think of plate tectonics as like Earth's way of sweating. It's Earth's way of getting rid of its excess heat, okay? This is just kind of a cool thing I wanted to show you guys. You know, the mantle does move. It is a softy, right? The mantle does deform, it does convect. And one thing where you can see this in real time is in Canada. So in Canada, believe it or not, Canada right now is rising up. It's getting higher. And you hear a lot of people talk about, like, oh, global warming, and the ocean levels are rising, and the sea levels are going to rise. But at the same time, Canada is actually getting higher. It's actually getting higher faster than sea levels are rising. Some places it's rising up 13 millimeters, you know, about 1.3 centimeters a year, which is pretty fast. So why on earth is that happening? And the answer is that 14,000 years ago, there used to be a lot of glacial ice. That was the last ice age, right? The Pleistocene. There was a lot of glacial ice on top of Canada. and that pushed down on the crust, it pushed down on the mantle, and it moved the mantle out to the side. Now that that ice is gone, the mantle is flowing now very slowly, but it's flowing back in to fill that space. And it's going to slowly push, and this is called glacial rebound. It's going to slowly push the crust back up, and you're going to get rebound and rising in some areas. So the crust is slowly rising in some parts of Canada. It's pretty cool when you think about it. So that has been happening, right? 0.5, in some places 0.5 inches, half an inch per year. It's pretty cool. So just to kind of show you guys, prove to you that rocks can bend and deform like butter. You know, they don't just break like cookies, they can bend like butter. You know, here are pictures. You've probably seen things like this, like in road cuts before, especially, I know like some of you have sent me like earth observations from, you know, Colorado, or trips to the Rockies, or trips to the mountains. You might see things like this, especially in mountainous areas, and it's just proof that rocks can bend. You know, you can actually see the bended rocks here. So rocks do convect, they bend, they deform if the pressure is high enough and if the temperature is high enough. So, you know, these rocks, what's really cool is when you see these rocks now at the surface, these rocks at some point were probably far below the surface. They were probably like 10 kilometers below the surface, but now they're up at the surface. So it just shows you, like, it's just crazy like how dynamic the earth is and how much it can change, where rocks 10 kilometers deep, like we've never even drilled down that far, you know, but yet earth can bring rocks even deeper than 10 kilometers up to the surface through erosion and through tectonic uplift. It's pretty cool. So anyway, rocks have been there, they've done that. Here's the rock cycle. I don't want to go through that too much because we've talked about rocks a whole lot. The earth flows, right? It flows from the grain scale to the rock scale to the mountain scale. Earth is flowing, and the rocks that seem like impossible, like it almost seems like biblical, you know, like the rocks are able to flow and move, and whole mountains will move, and whole valleys will be lifted up, and whole mountain ranges will be thrown down. You know, but it's true. You know, rocks do move, they do flow, and the whole mantle, in fact, the whole earth, the whole solid earth is flowing and moving and convecting. Okay, so it's a dynamic earth, and you know, you don't want to think of it as something just you know, static, that's just staying the same year after year. No, it's changing every year. Okay, so here's the recycle. I like to put this up here. Here's the recycle sign, you know, and I like to put it up there because to remind you that that's what Earth does. It recycles. It generates new material, new ocean crust at the mid-ocean ridges. It generates new lithosphere at the mid-ocean ridges, and then at subduction zones, that old lithosphere is destroyed and sinks back into the mantle. So it's this constant convective recycle cycle. Okay, recycling cycle. So there you go. This is a simulation. These are actual simulations of how Earth's mantle behaves, how it looks like a fluid, even though it is not a fluid. It is absolutely solid rock. Okay, so that's how it looks. And these like streams of blue stuff you see coming from the surface, that's the subducting plate. Okay, and the stuff that you see flowing from the core to the surface, that is the mid-ocean ridge. Okay, so anyway, that's kind of like some background, some review of things we've already learned, and some kind of overview of what plate tectonics is. Now I want to talk about and kind of spend the rest of the lecture on where did this theory come from, you know, who developed it, and it's kind of like historical evolution through time. And I'm going to spend the rest of the lecture doing that, and then next lecture we'll get into more details of plate tectonics. So I start off with this picture of this little charming fellow. This is an animal that's luckily no longer around. It's called Cynonathus. Cyno. Let me. Oh, it's spelled out here. So cyno. Whenever you see cyno like that, it refers to dog. So it's dog-like. Okay. Gnathus means jaw. So this fossil, this animal is named after, probably had a dog-like jaw, right? So and you can see it does kind of look like a dog, right? Now, this animal was found in Africa, Antarctica, and South America. So we find fossils of this little guy all around the world. However, this animal was clearly, you can just look at his morphology, the shape of his body. Morphology, by the way, just means shape of the body. You could look at his morphology and you can tell he's not a swimmer. You know, he's not in no way designed for swimming. So how could he have traveled across the Atlantic Ocean, across South America? So now you have to kind of close your eyes, kind of forget everything I told you for a minute about plate tectonics theory, and imagine that you don't know about plate tectonics theory. You are living, 100 years ago. You never heard of plate tectonics. You never heard of the idea that continents can move over the surface of the Earth. But at the same time, scientists are starting to find evidence of fossils, the same fossil found in multiple places. So how do you explain that, right? And there were a lot of different theories to explain that. But a lot of people have, over the years, kind of theorized that possibly continents moved around somehow. Maybe they didn't exactly know how. Maybe they thought they were ripped apart through Noah's flood or something like that. I'm not exactly sure. But it's an old idea that the continents were once connected. For example, this is from Thesaurus Geographicus, which is 1596. This is coming from the time of mercantilism, the time of not colonialism so much at this point, but just European sailors going all around the world, exploring the New World, and a lot of people were deeply interested in making maps, of course, and so maps showing the coast of South America at this time, people noticed that, boy, it sure does fit really well into Africa, almost as if they were once connected. So that was something that was well known. And maybe people theorized about it, hypothesized about it, say, isn't that strange? I wonder why that is. But nobody really came up with a very sophisticated hypothesis proposing that, yes, indeed, actually the continents were connected, until this gentleman came along in the 1900s. Okay, so we had to wait a very long time before somebody really proposed this seriously. So this guy, we're going to spend a lot of the lecture talking about this guy. This is Alfred Wegener. He was a polar climatologist, a German, and noticed that the east coast of South America, fit very, very well with Africa. And if you we learned about continental shelves last time, about how continental shelves are just extensions of the continent over the ocean. If you take into account the continental shelves, the fit is almost perfect. So you can see these light blue parts. These are the continental shelves. The fit is almost perfect between Africa and South America. So, Alfred Wegener noticed in 1910 that these two continents fit perfectly together. So he came up with this idea and worked on it for a long time. 1929, he published The Origins of Continents and Oceans, in which he laid out his theory that the supercontinent Pangaea was existed at however long ago. People were not sure how old the Earth was at this time. But he laid out this whole idea of the continents being once, at one time, connected. So in that book, The Origin of Continents and Oceans, he lays out his theory of plate or he didn't call it plate tectonics, he called it something else. He called it continental drift. Okay. So continental drift is sort of a precursor to plate tectonics. Okay. And he lays out 4 arguments, okay? Now, I just want to say something about your lecture assignment. So I have you summarize these 4 arguments in your lecture assignment. Please do not just copy these 4 words, okay? Do not just write matching coastlines, geology, glaciation, fossils, okay? That, I'm not going to give you points for that. And on the test, you need to understand these things more deeply than just 4 words. So you need to summarize and describe these theories and explain how they show continental drift, how they provide evidence for continental drift. Okay, so you don't need to write an essay for each one, but you should write sentence or two. And that's generally about the lecture assignments. Most of you do really well on them, but the key to doing well is just taking the time and explaining. People lose points because they don't explain themselves. They abbreviate things, they write down one-word answers. Just make sure that you're explaining yourself fully there, because I need to see, you might know that you know it, the answer, but I don't know that you know it. So I need to be able to see that you really understand what's going on here. So anyway, just a little advice on that. So matching coastlines, geology, glaciation, fossils. These are the 4 lines of evidence that Alfred Wegener provided to prove his theory of continental drift, which is the idea that continents have moved over time. They weren't just established in these one areas and existed all through geologic time that way. No, they've been moving. It's a dynamic Earth. Okay. So first of all, matching coastlines. I think that you understand very well how matching coastlines proves continental drift, so I'm not going to go into it there. I think it's pretty intuitive for people to understand. Another observation, those matching geologic units. So if you look on the coastlines of different continents, along the boundaries where the continents would have been connected, interestingly, you find very similar geology. Look right here, like Africa and South America. You can see that you find this particular rock unit. And look how, if you match them together, they really connect very well, okay? So you find the same kind of rock on Africa as on South America. That's pretty interesting, right? Also, you find the same mountain belts, and you find the same kind of direction of like how the mountain chains are actually oriented. Do you see how the mountain chains here are oriented in this kind of like, what is it? I guess northeast, southwest sort of orientation. And notice that the orientation is the same on Africa here and on South America, where they would have been connected. So that was pretty interesting, right? The same thing you can say about North America and the west coast of Africa and Europe, right? They share a lot in common in terms of rocks and the kind of geologic units you find. By the way, you could have whole classes devoted to this subject, but there are like a lot of rock units that are exactly the same in Europe as in North America. One thing I'm thinking of, for example, is the old red sandstone. It's a rock that was used a lot in Europe to make castles and make building supplies, and you find the exact same kind of sandstone in North America as well. So matching geology, matching mountain belts, matching geologic units, that all proved Alfred Wegener's point that the continents were connected at some point. Just to kind of drive it home, like I just think, look at the topography and look at the shape of the mountains in West Virginia and compare it to the Scottish Highlands. And again, these are 2 areas that would have been connected at one time under the theory of theory of continental drift. So you can see that the topography really looks similar. Like they look like similar sort of places, and you wouldn't necessarily know you're in Scotland versus West Virginia looking at it. Okay. So observation number 2 comes from glaciation. Now we just got finished studying glaciers, right? I think just like 2 weeks ago or so. So that glaciers can scour and shape the landscape. Remember we learned about, like, this is, for example, Yosemite's Half Dome here. You can see the big U-shaped valley here. You can see the horns and arêtes and things like that. So that they leave these scour marks and scratches and striations on the surface. So what is cool is that you can figure out the directions of glacial movements. You can, and of course glaciers leave a lot of evidence for their existence. They leave a lot of stuff behind that we can collect later in the modern era and tell that, oh yes, there were glaciers here. And this is the direction the glaciers were moving in the past. And what do you find? Well, you find that the glacial movements, if you connect all the continents back together, the glacial movements really kind of match up and they agree. So it's also interesting on top of this to note that in India, you can find in equatorial Africa, in equatorial or near equatorial South America, you can find a lot of evidence of glaciers. And that's a little bit interesting because you know that India is near the equator. How could you have glaciers on the equator? Of course, there have been times in Earth's history, there have been, well, I shouldn't say there have been, but there have possibly been times in which the entire Earth was frozen over, but it's conjectured. But anyway, there's a lot of evidence from glaciers to say that, yeah, these were connected at one point. So, or I should say the continents were connected at one point. And a fourth line of argument comes from fossils. So I pointed out Sinognathus already. There's a lot of different very specific fossils. Another one I could mention here is Mesosaurus. So Mesosaurus was a little, he's a little swimming reptile. He wasn't very big, so you can't really tell from this picture, but he was maybe just like a foot, kind of like 15 inches long, maybe 2 foot long, something like that at most. So he was a swimmer, but he wasn't a big like transatlantic swimmer probably. So Mesosaurus is found in Africa and in South America. Now, one thing that is interesting, you might say, okay, well, maybe he swam across the Atlantic, and maybe he did. But isn't it interesting that Mesosaurus was capable of crossing the Atlantic, theoretically, right? Could cross the Atlantic, but couldn't go further north into Africa, couldn't go further east into Africa, couldn't go further north into South America. That seems a little weird. You know, like his range is fairly restricted on the continents on which he is found, but it's gone across the Atlantic. A little odd, I would say. So that's Mesosaurus. There's also other fossil species. Glossipterus, for example, is a type of fossil fern. Okay, ferns are not known for making transatlantic journeys. So, evidence from plants as well can be very persuasive in terms of proving continental drift, and Alfred Wegener's case for continental drift. So, anyway, what happened to Wegener and his theory? Well, it's kind of just a tragedy of life, of science, that Alfred Wegener died before any of his theories were accepted. You have to understand that at this time, this was a very new theory. And it was wildly, although we accept it without even thinking about it was wildly radical at the time that it came out. I mean, just like sit and imagine, like, let's say you never heard this stuff before, you never heard of plate tectonics before. Imagine someone saying, hey, you know what I think? I think that, the continents have moved over time. I think that the whole mountain belts have plowed through the Earth and they've shifted. I think that's Antarctica used to be at the equator. Like, could you imagine anything crazier sounding than that? Like, it sounds fantastical. It sounds like a fantasy novel or something, or fairy tale. But it's true, And that's how you always know. I mean, to me, you always... It's interesting because the actual reality is often stranger than fiction, and that's kind of a cliche, but it really is true. It's you can kind of tell a man-made idea, a man-made theory compared to reality in science, because a lot of times the reality is so strange you would never have thought of it yourself. So anyway, Alfred Wegener was in that category, an idea that was so strange, so radical, it was not accepted at the time. And so he was rejected. He was roundly rejected because he couldn't explain. He came up with, of course, a lot of evidence for how continental drift could have happened, but he couldn't explain a mechanism for how it could happen. He could show that it happened through a lot of evidence, but he couldn't explain the how. He couldn't explain the mechanism. We didn't understand, and he did not understand how it could happen. He just knew it was true. Okay, and that's like a lot of things in life. You know something's true, but you can't always explain how you know it or how it could have happened or whatever. But for that reason, he was rejected, and he was rejected for about 30 years after his death until he was finally sort of vindicated in the later years in the 1960s. So Wegener died on a research trip to Greenland. Whenever you see him, he's always smoking a pipe, and people think that actually just the stress on his lungs and his body from too much smoking really contributed a lot to his early death. So anyway, Wegener had to wait for his vindication, post-mortem vindication, till the 1960s, 1950s, basically after World War II. A lot of geophysical evidence came up that helped explain how plate tectonics could happen. Okay, remember that's what was stopping Wegener from being accepted at the time. He couldn't explain how. So let's take a look at the geophysical evidence that arose after his death. The geophysical evidence that shows the mechanism behind plate tectonics and continental drift came after World War II. There are three main lines of evidence. One is from echo sounding of the ocean floor. Another is from magnetic anomalies. Another is from seafloor age. Again, on your lecture assignment, be conscientious that places, I think I ask about these three mechanisms, or I'm sorry, these three lines of geophysical evidence, and they're not. It's not sufficient to just state these three things. You have to learn about them, understand them, and explain them on your lecture assignment. So anyway, let me explain each of these in turn, because they're probably like just very strange terms. Like what are the, like magnetic anomalies especially is very strange. So let me give you a little background in where this takes us. So okay, imagine it's World War II. We have these German U-boats that are patrolling the North Atlantic, and they're a huge threat to Allied naval convoys and to transports and ships. And we are deeply interested at this time. The Allies are deeply interested in learning about the depth and the shape of the seafloor, right? Because we want to search for U-boats. We want to know where the depths are. We want to know the shape of the topography of the seafloor. So at this time, there was a man named Harry Hess. He was a captain of an assault transport, Cape Johnson, during World War II. He made a lot of very interesting observations about echo sounding the seafloor, and a lot of interesting observations about the shape of the seafloor in his many voyages across the Atlantic. So after his service in World War II, he became chairman of the Department of Geosciences at Princeton. So he took this knowledge that he gained from his naval service and started exploring the seas again. And the way that he did this is he took a big research vessel like this. He had an air gun, creates a huge seismic echo in the ocean. The echo bounces off the bottom of the ocean floor, and it's picked up by these recorders, okay? And the time that it takes for the echo to bounce off the ocean floor and come back, that gives us the depth of and the shape of the ocean floor. Just like bats and other animals can really very successfully use echolocation to understand the shape of a cave or a shape of trees and things like that. So same principle. We're using echolocation to figure out what the shape of the seafloor is. And we put all that information together and process it all together. We can figure out exactly how deep the seafloor is, and we can image it out three-dimensionally really well. So that's just kind of the same process. Some of you might have like a fishing boat with a fish finder on it. Fish finders work the same way. They send out an acoustic pulse. It bounces off the fish, and it comes back to you, gives you a little information. And it can also, as fish finders now can also image out the ocean floor pretty well as well. So that's exactly what we're doing here. So exploration of the seas, echo sounding, it's how we mapped out the bottom of the ocean. So this was done in a huge way during World War II, after World War II, the decades following. And maps were compiled of the ocean floor, and what we found, it was pretty interesting. So imagine we don't really know. At this point, what did we know about the ocean floor? You know, you saw what we learned about the ocean floor in 1870s. We had, you know, the Challenger, a sailboat going around, dropping a weighted line into the ocean to figure out how deep things are. You know, pretty primitive techniques. And you know, that's just all about what we knew about depths of the ocean. So now we get these very detailed maps about the ocean depths. Okay, so let's look at this map. Now, what do you see? So we see the continental shelves, right? They're very shallow. They're maybe just no deeper than maybe 500 meters, which I know that sounds pretty deep, but it's nothing really compared to the abyssal plains. You get these very deep parts of the ocean go down up to 5,300 feet, probably 4,500, or I'm sorry, meters, not feet, meters. So probably 4,500 meters is average, but 5,300 you can get down even that deep in these abyssal plains. Then you find in the middle of the ocean something really pretty crazy. You find a mid-ocean ridge, right? An NMOR, a mid-ocean ridge. This is a 2 to 3 kilometer high, so about 10,000 foot high mountain range in the middle of the ocean. And think of how shocking that must have been. To go, you're doing these cruises of the ocean, and you find these mountain chains that are larger than any mountain chain on Earth that we found on the continents, and it's right in the middle, underneath the water, right in the middle of the oceans. So what is it? Where did it come from? Why is it there? Those are all the pressing questions that start to build up in people's minds. Okay. Now, the idea is that, well, you'll see later, is that the oceans are basically symmetrical about this ridge. So it's almost like you could fold the oceans back up and crease it along the, you know, fold it along the ridge, and they're the same on either side. Okay, that was really interesting. So it shows that the Earth is spreading, the Earth's crust, the ocean crust is spreading from this ridge. Okay, so that was an interesting data point that we have now after Alfred Wegener's time. Okay, another piece of evidence that came to bear on this question of whether continental drift really happened or if it was just an anomaly or coincidence that explains Alfred Wegener's observations. Another piece of evidence that comes to bear comes from what are called magnetic anomalies. Now, you know, I've explained this many times before in the past in this class, that we have a magnetic field that is generated by the outer core, the convection of the outer core. We have a magnetic field. Now, it might interest you to know that the magnetic field has not always been stable over Earth's history. In fact, sometimes it has reversed. Sometimes the South Pole becomes the North Pole, and the North Pole becomes the South Pole. And we have found that Earth's magnetic field does this periodically. It has a reversal. And this happens maybe every, it changes a lot. It's not stable, but this happens maybe every 700,000 years. It will be reversed, so you'll get reversals. Okay? So that's a thing that happens. Now, you also hopefully know from our minerals lecture, sorry, we're combining a lot of stuff, right, that we've learned about in the past now, oceans and the Earth structure, now minerals here. I hope you remember that there's a mineral called magnetite that is very common. It's very commonly found in basalt rocks, like the kind of rocks that make up the seafloor, and it's magnetic, okay? So this magnetic. So what happens is that when there's a magnetic field, so I'm going to draw a magnetic field. Okay, here's Earth's magnetic field. Okay, pointing to the north, right? So there's the magnetic field. When you have these magnetite, now let's say we also have a blob of magma. Here's my blob of magma, okay? Now, of course, you can't see Earth's magnetic field, but there's a blob of magma there, okay? Now, imagine that you have all of these little flakes of magnetite that are in the magma. As the magma cools and these little flakes of magnetite are there, they are going to orient themselves with regard to the magnetic field. So they're going to be oriented to the magnetic field. So there's all the magnetite grains that are in my blob of magma. So when the rock cools and crystallizes, what you end up with is a rock that has recorded the direction of the magnetic field over Earth's history. So whether it's pointing to the north, but sometimes the magnetic field is not pointing to the north, sometimes it's pointing to the south. So because sometimes it reverses, right? It can reverse. Okay, so what you're going to find is that rocks of the seafloor provide a record of the direction of the magnetic field at the time that they cooled and crystallized. So you end up with a complete record of magnetic pole reversals over Earth's history. So this is done today. This is how it's done. You have this thing that looks like a proton torpedo or something. It's not a torpedo. It is actually a magnetometer. And we can actually read the orientation. If, believe it or not, this boggles my mind. But this device is so sensitive to magnetic fields that it can actually pick up the orientation of the magnetite grains in the ocean floor below. So it can tell you whether the magnetite grains in the ocean floor below were oriented towards true north or reversed. Okay, so it's pretty amazing technology, but that's what we do. We drag this magnetometer behind a ship, and it picks up on the orientation of the magnetic orientation of the magnetite grains below on the seafloor. So what do you find? So you drag this thing over the seafloor. You find that some of the magnetite grains are pointed to north, some are pointed south. Some are pointed north, then you hit another area, they're pointed south. Then you hit north and south. So it's just picking up the periodic reversals. Okay, now that's useful, that's cool. How does that prove continental drift? Well, this is how. If you look along the mid-ocean ridge, you see that the pattern of magnetic field reversals recorded in the seafloor is exactly the same on either side of the ridge. And what's cool is that it's like a barcode, like, right? Doesn't that look like a barcode, like a HEB or something, you know, you put on the back of your food? It's like a barcode, and it's exactly the same on either side. And it proves that the ocean floor was created symmetrically, spreading from this ridge. So the whole idea of seafloor spreading was proved by these magnetic anomalies. And seafloor spreading gave us a way of saying, yes, here is a mechanism that shows how continents could have moved over Earth's history. It could have been from the spreading of the seafloor. Now, the last piece of geophysical evidence came from radiometric dating. Okay, radiometric dating provided further evidence for seafloor spreading. It was kind of like the nail in the coffin that really proved that, yeah, this is a thing. Continental drift is a thing. Plate tectonics is a thing, and seafloor spreading is a very important process on Earth's surface. So when we finally developed the technology to date the seafloor, we found that around mid-ocean ridges, the seafloor is very young, maybe just thousands of years old. But as you moved away from the ridge, now look at here, the Atlantic's perfect, right? It's very young along the ridge. As you get progressively closer to the coastlines, it gets older and older and older and older and older. Okay, so that showed that, yeah, the seafloor is spreading. The ocean crust close to the coast is old. As you move towards the ridge, it's very young. Seafloor spreading is a thing, and it proves a mechanism of how continental drift could have occurred. Okay, so we start off with a little baby mid-ocean ridge. As it gets older, the seafloor spreads, and it spreads and spreads. And as it spreads, it pushes continent A and continent B, or continent A and continent B here, away from each other. Okay, and that's how continental drift occurs. Okay. So, oh, I just wanted to show you a little video here. Let me, you know, my thing never works here. So let me go look this up on YouTube. Oh gosh, let's see here. YouTube. And I want to look up, sorry you're seeing all my personal stuff here. I want to look up volcanoes. Yeah, so I want to show this to you. It's pretty cool. These are underwater volcanoes. And so this is what's happening at mid-ocean ridges every day. Okay. And 80% of our lava or volcanic eruption. Oh, actually, let me turn this on really loud so you can hear it. I think I have it on quiet. Here we go.
Racing on the Joint Institute for the Study of the Atmosphere and the Ocean at the University of Washington. I was the chief scientist on this expedition, so I led the cruise and the trip to the West Mata eruption. The video that you'll be looking at is large magma bubbles. They're about 3 feet across, and the bubbles are molten rock that are expanded under the pressure, the gas pressure of magmatic gas. And the magmatic gas, we presume, is mostly water. And when the water is under the magma, it's at magmatic temperatures, thousands of degrees. And when it's suddenly cooled by coming in contact with seawater, the bubble bursts. So what excites me the most about this volcanic eruption is that that on planet Earth, this is a process happening all the time. And yet, we have never seen it happening in quite this way. The ocean floors are formed almost exclusively by volcanic activity. And strangely enough, we really have never seen molten lava flowing on the seafloor from a submarine volcano. We have seen in other eruptions much shallower in the ocean, but in this case, we're actually seeing molten lava flowing on the seafloor. We're seeing these magma bubbles. We're seeing these explosive events. We're seeing the seafloor open up and pour out magma, and we're seeing these pillow lavas, probably one of the most common forms of rock on Earth. And despite the fact that this happens, 80% of the volcanoes, 80% of the eruptions basically on Earth are happening underwater. And we've never made these observations before.
Okay, so that's video of underwater eruptions. And that's what's going on every day at mid-ocean ridges. So you constantly have mid-ocean ridges ejecting material like that. Okay. So seafloors are spreading. How can the whole continents move across the surface of the Earth? It's because the mantle beneath the continents is undergoing convection. Now, around this time, another big discovery that occurred in mineral physics is that it showed that even though the mantle is solid, that it can convect. And that finally kind of really showed, yeah, this is how this happens. Mantle is convecting, and it's powering plate tectonics. Mantle convection is powered by the geothermal gradient, by the very hot, temperatures at the core mantle boundary compared to the relatively cooler temperatures at the surface. Okay, so it's Earth trying to cool off, and it does it through convection, and the convection powers this plate tectonics. So that's how this happens. There's the convecting mantle. You can see the blue spurts of crust being ejected into the mantle here, right? That's the subduction of the seafloor. You can see these hot plumes come up from the core. Those are what ultimately become mid-ocean ridges, okay? So that's the end of this lecture for today. I hope you enjoyed it. We're going to be talking about more details of plate tectonics theory. In the meantime, I wish you a happy day, good day, and I hope that you do well in your lecture assignment, and please let me know if you encounter any troubles whatsoever. I'm here to help you, so always remember that it's my job to help you, so you should never feel shy or hesitant about reaching out for help. So I will talk to you next time.